Let's continue our discussion of reactions with redox. Redox stands for oxidation reduction reactions. Now, this is a very common type of reaction, much like the double displacement is a common type reaction. But unlike a double displacement reaction, in an oxidation reduction or a redox reaction, we have a transfer of electrons. So oxidation is the loss of an electron. So if you lose an electron, you are oxidized. Reduction is the gain of an electron, which means if you gain an electron, you've been reduced. Here's the thing. They cannot happen independently of each other. If you lose an electron, it must go somewhere. If all of a sudden you gain an electron, it must have come from somewhere. So redox is completely linked. Oxidation and reduction. You cannot have one without the other. Now, ways to remember oxidation is the loss of an electron and reduction is the gain of an electron is one way, Leo goes Ger. Lose electrons, oxidation. That's Leo. Gain electrons, reduction. That's the Ger. Or another way is oil rig. Oxidation is loss and reduction is gain. Now, in order to understand a redox reaction, we have to determine the oxidation number of each of the species present in our reaction. This is going to allow us to kind of bookkeep the electrons so that we know where they're at and where they're going. Now, here we have a reaction, magnesium plus oxygen. This was Mg plus O2, giving me 2 MgO, and I gotta have a 2 there, right? This was what we had called a combination or a synthesis reaction. But it's also a redox style reaction because magnesium is losing electrons to oxygen. Oxygen is gaining electrons. So in this case, magnesium is oxidized and oxygen gets reduced. So let's take a look at how we determine the oxidation number for all of the species present. So as I stated, this is a bookkeeping for charge or bookkeeping for electrons. It has rules. Now these rules are actually pretty simple. You just have to remember a few of them and you'll get the hang of how to do this. So any element in its free state has an oxidation number equal to 0. So if I were to write an equation, oxygen has an oxidation state of 0. Or chlorine has an oxidation state of 0. So any element in its natural free state, oxidation number of 0. And that actually goes for both atoms present in these diatomics. Both oxygens have an oxidation state of 0. Both chlorines have an oxidation state of 0. It's not just for your anions. For example, if I had iron, that would have an oxidation state of 0. Okay? So, that's the first one. Elements in a free state have an oxidation number of 0. If you have a monatomic ion, it is going to equal the ion charge. So, let's take a look at what if we had the O2 minus ion. That means its oxidation state is 2 minus. Or if we had the Fe2 plus ion, its oxidation state would be 2 plus. Now, a neutral molecule must have a sum of oxidation numbers equal to 0. This is the balancing of charge, and we've seen this before when we were writing equations, or not equations, but writing formulas for our ionic compounds. And similarly, if we have a polyatomic ion, the sum of all the oxidation numbers must equal the ion charge. And then we've got a couple of elements that we have to deal with. Fluorine, if it's in a compound, will always have a -1 oxidation state. Oxygen, if it's in a compound, is usually going to be a -2 unless we have a peroxide ion, in which case it's a -1. Which, you can think about it this way. The O2 2- ion, that's the peroxide ion. Each oxygen represents a -1. And hydrogen is a +1 unless it's an anion, in which case it's a -1. So let's do a few of these compounds to get a hang of it. Alright, so here we have a series of compounds: sodium chloride, magnesium oxide, the sulfate anion, nitrogen dioxide, and water. Starting with the sodium chloride, the sum of oxidation states in a neutral molecule must equal 0. Now, here we have sodium, which is usually going to be a cation of +1 charge, so Na plus, and then the Cl had a 1 minus. So these are actually the oxidation states. Sodium has an oxidation state of +1, and the chlorine has an oxidation state of -1. In magnesium oxide, again, the sum total must equal 0. Now, that means that the magnesium, which is usually a 2+, and the oxygen, which is usually a 2-, give us oxidation numbers of +2 and -2 respectively. Now let's take a look at something like the sulfate ion. In a polyatomic ion, the sum of all of the oxidation states must equal the overall ion charge. So here we have the sulfur, which it's not an ionic compound, even though it's in a polyatomic. It's not an ionic compound. That's actually a molecular sort of bond going on there. But we've got the oxygens. Now this is artificial bookkeeping. If oxygen is in a compound, we usually say it's a -2. So it would have an oxidation state of -2. Now, let's take a look. I've got how many -2s? I've got 4 of those guys. So 4 times a -2 gives me a -8. Now, the sum of the oxidation states must equal -2. So the sulfur must be a +6. Now, I know that sounds really weird, and it is. But remember, this is an artificial bookkeeping. It is not a real charge. It's just a way of thinking of the charge that could occur on these atoms. So what about in NO2? In this case, we've got the nitrogen and we've got the 2 oxygens, which again, these, as the oxygen is a -2, we've got 2 of those guys, so 2 times a -2 gives me a -4. So our oxygen is a -2, but our nitrogen then must be a +4. Again, it's not a real charge. And in water, we've got hydrogen and oxygen. Hydrogen is usually a +1, unless it's the anion. In this case, we'll look at the hydrogen as being +1, and the oxygen as being -2. So +1, and then -2 for our oxidation states. You'll get better with these with a lot of practice. Now, there's some other terminology that can be a little bit confusing, and that is the idea of the agents. The agents are going to cause something to happen. So a reducing agent is something that is going to cause reduction. By causing reduction, that thing must be oxidized. So whatever substance is oxidized, that is your reducing agent. Similarly, an oxidizing agent causes oxidation, and therefore that substance must be reduced. So here we have a series of pictures of the beakers where we have zinc in a copper sulfate solution. Now what happens is a single replacement style reaction. Surprise, surprise, that's another redox style reaction. Where the zinc goes from being an element, a free element, to being in a compound. So the zinc actually goes from being a 0 to a zinc 2+. So what happened? How do you go from being a 0 to a 2+? You have to lose electrons. It loses 2 electrons. So since it loses electrons, the zinc is oxidized. Since the zinc is oxidized, the substance that is oxidized is the reducing agent. So zinc is oxidized, and it's the reducing agent in this case. Now the copper, on the other hand, the copper over here, that goes from being a 2+, so Cu2+, to being a Cu metal, a Cu0. So it must have gained electrons. Since it gained electrons, it got reduced. So the copper is reduced, which means it caused oxidation, so it is the oxidizing agent. Now, what do you think is going on here in this slide or this picture? We have silver and copper going on. So tell me, who gets oxidized, who gets reduced? So I'm taking a piece of copper wire and putting it in silver nitrate solution. So the copper goes from copper 0 to copper 2+. So what is that? The silver goes from being a silver plus to silver metal. So it goes from a plus to 0. So what happened to the silver? Was it oxidized or was it reduced? Does that make it the oxidizing agent or the reducing agent? Now, the final thing about redox for us at this level, Chem 130's got a lot more redox. They've got what's known as the electrochemistry chapter, which is a lot more in depth with redox reactions. But one of the easy things to do for us to be able to determine who gets oxidized and who gets reduced is to split into what we call half reactions. So what we're going to do is we're going to split up this reaction, the zinc solid plus copper 2 sulfate going to zinc sulfate and copper solid. So we're going to take a look. The zinc was in a 0 and it goes to a +2. So it lost 2 electrons. So -2 electrons. The copper went from being a +2 to a 0. So that was a +2 and goes to a 0. So this actually gained 2 electrons. So +2 electrons. Now if I look just at those ions, take a look here. The zinc can be thought of as going to zinc 2+ ion and giving off 2 electrons. So here zinc must be oxidized, which makes it the reducing agent. And we can split that copper half reaction into the copper 2+ gaining 2 electrons to make copper metal. In this case, gaining in the electrons means that the copper is reduced. Since it is reduced, it must be causing oxidation or is the oxidizing agent. Half reactions become a lot more important when trying to balance redox-style reactions. Many redox-style reactions, especially involving more than just single replacement style reactions like we've looked at, can be very, very difficult to balance. So this is one of the easy ways to balance these redox reactions. We don't have to worry about that in here. We're going to just keep our focus on the redox style reactions that are pretty simple. Okay? So I hope you understand redox a little bit better. This is a very confusing style of reaction, and I understand that. So please watch this video over and over again to make sure that you understand. If you have any questions, please bring them up to me in lecture.